Okay, tonight we have Suyang Xu from the Department of Chemistry and Chemical Biology at Harvard. He will be our speaker. He's going to tell us about new topological phases of matter. Suyang.
Okay, yeah, thank you very much, Professor Westerveld, and good evening, everyone. So my name is Suyang. I'm a junior faculty member in the Department of Chemistry and Chemical Biology. And today I'm very happy to tell you about our research, and I'll probably focus more about our recent work on this so-called topological Axion insulators. I'll try to explain what it is, but I also talk a little bit more generally about what in the lab, what we care about and why it is broadly interesting for fundamental science. Okay, now, okay, so here is the outline of the talk. So first, I'll try to explain what is Axion, and then I'll try to explain what is a topological Axion insulator, and then talk about our work. And finally, I'll talk more broadly about the entire research of our lab. Okay. Okay. So first, let's do Axion. Okay. So let me pose this question. So, what does the strong force subatomic interaction, fundamental symmetries, laundry powder, and a piece of quantum material, what do they all have something in common? So it turns out that they can all be related to a fundamental particle that actually haven't been found in the universe, that is called the axion. Okay, so let me first explain what is axion. So I'm going to tell you a very interesting, sort of just like a story in high energy physics. And then I'll then try to say why it is related to condensed matter and what we do in materials. Okay, so so let's go. Okay, so we know that in physics, symmetries are very important. For instance, in condensed matter, we talk about crystal symmetries and stuff like that. In high energy physics, we talk about the law of physics, being invariant or not invariant under certain symmetry operation. And it turns out that when we try to understand subatomic interactions, the following three symmetries are very important. The first one is parity. So parity, we can think about, we have our universe and we put it, with respect to a mirror, then, we have the mirror partner. So then we ask if we have some physics law in this universe, whether it is the same law in the mirror reflected universe. Okay, so mirror also we can think about space inversion. So they are kind of interchangeable in high energy physics. Okay, now second one is charge. Charge, thinking about if I flip a positive charge to negative charge or vice versa, whether the law of physics is the same or not. And the third one is called the time reversal. It means that if I reverse the direction of the time arrow, whether the physics is invariant or not. Okay, so it turns out, for instance, for QED, like quantum electrodynamics, all three symmetries are respected. But when we go to more higher energy interactions, for instance, inside the nuclei, when we talk about subatomic interactions, then those symmetries could be broken. What is up to now, what we found is always preserved is the product of the three. So CPT symmetry, when we reverse the charge, reverse the space, and reverse the time, reverse all three together, then the law of physics is always invariant. But if we only reverse, let's say C and P, then the physics can be actually not invariant. And it turns out that this has been found in the weak force. The weak force essentially is a subatomic interaction, and it's mostly relevant to, let's say, nuclear fission. Okay, so it turns out that in the weak force, this CP charge and parity combined symmetry is broken, and that was first proposed, I guess, in the 1940s or 50s two theorists, Yang Zhenning and Li Zhengdao. And then, it was, they proposed that the parity symmetry can be broken for the weak interaction. And then the experiment was done by a professor in Columbia, Wu Zhenxiong. And she did the experiment. Basically, she studied the nuclear fission of cobalt 60, okay? And she found that this fission process breaks parity symmetry. And later on, they found that the same experiment actually also break charge symmetry. So then combined C and P is also broken. So essentially, people have found CP violation in weak force. And when they look at the theory, the corresponding theory for the weak force is like this quantum flavor dynamics. That also allows the CP violation. So theory predicts it, and experiment find it. So everything is consistent. So naturally, then we know that in the subatomic interaction, there's weak interaction, but there's also strong interaction. So then a very natural question would be, what about the strong force, okay? Like interaction between quarks. Would they be also CP violated? Now, we know that by the way, so what I'm talking about in high-energy physics, just treat it as a story. I found it fascinating, but those details is not very relevant for us. But you see that there are actually crucial aspects that are related to condensed matter. Okay, so now we know that the fundamental principle for this strong interaction is this QCD. Okay, so now in the QCD, the fundamental theory actually almost require the breaking of CP symmetry, and it is because in Lagrangian of the QCD, there is this term that is this theta term. There's a theta and there's a electric field dot product magnetic field. So if this term is non-zero, which in general it should be, then the physics of QCD, the physics of strong interaction, should break CP symmetry. However, people did many experiments, and experimentally, they found no signature of CP violation, okay? And this is actually a very, very important problem, fundamental problem in the particle physics and high-energy physics. And there they call it the strong CP problem. And one of the most important predictions for CP violation in strong force is that if CP is broken, the neutrons should have an electrical dipole, okay? So this is very interesting because usually when we think about protons or neutrons, we just think about like a spherical ball, okay? That's the most reasonable and most, natural kind of picture. But if the neutron has an electrical dipole, that would mean, we know the whole neutron is charged neutral, right? But that would mean that inside the neutron, there is charge distribution. Let's say the top part of the neutron has more positive charge, and the bottom part of the neutron has more negative charge. Then there will be an electrical dipole. And that's very surprising because we usually think the neutron is kind of like an isotropic kind of particle, okay? So, or in other words, if there is an electrical dipole, then we can say that a neutron will have an electric field, okay? We also know that neutron has a spin, so it has a magnetic field, okay? So if this prediction is true, that means the neutron will simultaneously has a E and a B. And that you can also see, that just means that if we have this term in the Lagrangian, then we have an E dot B term. And this is, you can see, is a natural consequence of an E dot B term, okay? However, in high-energy physics, we can measure this magnetic dipole or electric dipole very, very precisely of fundamental particles. And so far, we found no signature of electric dipole in the neutron. Or we can say that if there is a small dipole, that will be 1 trillion times smaller than what it should be according to QCD, okay? So this is actually another very famous problem in high energy. This is called the neutron electric dipole problem, okay? Now, okay, so basically the problem is here, theory predicts that neutrons should have a dipole according to QCD, but experimentally we found no electric dipole. So then some group of theorists, they thought, okay, maybe, you know, we have this Lagrangian, but maybe theta just happens to be 0, okay? If theta is 0, then we don't have this term. Then everything is fine again. But then, you know, physicists don't like just, you know, coincidence. They don't like just, okay, this term just happens to be 0. So they don't like this explanation. So then in 1996, these two professors at Stanford, Pachin and Quinn, they proposed another interesting idea. They say, okay, what if I don't treat theta as a fundamental constant, but I treat theta as a field, as a potential field. And the theta has an energy minima, has a potential minima when theta is 0. So then, in order for the whole system to, you know, minimize its energy, it will naturally, theta will naturally go to 0. So that's called the Pachin and Quinn theory. And shortly after that, Frank Wilczek, a famous Nobel Prize winner at MIT, he immediately realized that now because theta becomes a field and the quantum oscillation associated with the potential field will generate a new particle. Or in other words, because now theta is a dynamical field, then that naturally means that we will have a corresponding new kind of particle. And he called this particle axion. And there was a very interesting story. He sort of talked about it everywhere in his talk. The reason that it's called axion is when he was very young, when he was a student, he saw in the supermarket, there's one kind of laundry powder, and the brand is called Axion. And he said, oh boy, it looks like a name of a particle. If in the future I become a physicist and I discover a particle, I'm gonna name it as Axion. And he did that, okay? So now we all call it Axion, okay? And this Axion then would basically be the solution that can allow us to solve this neutron electric dipole problem, because it would, you know, minimize the theta at 0, okay? And it turns out, very interestingly, once people start to theoretically study this kind of effect of the axion, they found that axion is very, very light. Its velocity is close to the speed of light. It has no spin, and it doesn't interact with most of the fundamental particles. So therefore, it's a very, very good candidate of dark matter. So now there are many other, you know, physicists in the cosmology trying to search for axions in hope to hunt for dark matter. Okay, so now axion is, you know, this. So far we haven't found it in particle physics, but you know, this is very interesting and it's one elusive particle that can clean up two fundamental problems. Okay. Okay, so now let's talk more about condensed matter. So now we talk about this interesting particle in high energy. Why is it even relevant to condensed matter physics? Okay, so in order to appreciate topological axion insulator, we can think about from these two perspectives. One is, you know, we all learned electromagnetic theory, right? We like Ampere's law, you know, Coulomb's law, this kind of thing. So we think about the electromagnetic response of matter or of materials, okay? The other one is think about the concept of quantization, okay? So let's think about E and M, okay? We all learned E and M. For instance, we know that according to the Maxwell's equation, if we have any dielectric material, we apply an electric field, we can generate inside the material an electrical polarization. Think about, you have, you know, a piece of silicon dioxide or any insulator, okay? You apply an electric field, what will happen is that you will separate positive and negative charges inside the material, and as a result, the material will respond with a macroscopic electrical polarization. And we can define P equals to a coefficient multiplies E. This coefficient chi, we also call it the, you know, the dielectric susceptibility, okay? Now, also we know, for instance, if we apply an external magnetic field, then even if we have a, you know, a paramagnetic material, but when we apply a magnetic field, then we can generate a magnetization. So in the E and M, or in the Maxwell equation, we write M, which is the response of the material, equals to chi multiplies H, okay? So this makes sense, right? I apply electric field, and then I generate electrical dipole. I apply magnetic field, I generate inside the material magnetic dipole, okay? So this happens in all sort of materials, that conventional materials that we know of. But it turns out that there is also this actually very unconventional response that is the cross-coupling term, okay? So we can think about in some very strange material, I apply an electric field, but I can generate magnetism. I can generate magnetization. Or I apply a magnetic field, but the material responds to this magnetic field with an electric polarization. So that, if you're familiar with the Maxwell equation, you see that it doesn't actually exist in the regular kind of Maxwell equation of matter, okay? So this cross-coupling term is what we call the magnetoelectric response. So that magnetoelectric response only exists in a very special class of materials, not the conventional materials that we know of, okay? And it turns out that this electromagnetic response that I'm talking here has a natural one-to-one correspondence with the QCD Lagrangian, okay? So this is the QCD Lagrangian that I'm showing it again. And it turns out that we can also write down the electromagnetic Lagrangian of any regular material, okay? Or basically, this is just a fancier way of writing Maxwell's equation for a dielectric or a regular material, okay? But it turns out very recently, in 2008, these theorists at Stanford, they figured out that we can add an additional term in this E and M Lagrangian of materials, which is formally, it directly resembles the theta term in the QCD. It's also a theta term, and it's also E dot B, okay? And what it means is that now in condensed matter, we can also have this theta term and this E dot B interaction. And when theta equals to 0, then this term is irrelevant. And that goes back to, what I just talked about, those conventional electromagnetic response. And when theta can now, remember that I just showed you that theta can be a field. Now, if we impose some symmetry, for instance, if we ask the crystal to be central symmetric, then we can show that theta can only be either 0 or pi. So for most of our materials that we know of, theta equals to 0. Theta equals to 0 means that this term is irrelevant. It doesn't exist. Or in other words, we don't have this coupling, okay? But there can be a very strange kind of material where theta actually equals to pi. And that is precisely the topological Axion insulator that we're trying to search for. When theta equals to pi, that means inside the material, the electrodynamics or the electromagnetic response of the material is fundamentally different because it has this additional term. And the consequence of this term is basically it allows this cross-coupling. It allows this magnetoelectric coupling. And actually, not only in topological Axion insulator, it allows this kind of coupling. It actually allows it in perhaps the most dramatic way, in the sense that the magnetoelectric coupling is quantized. So what do I mean by that? So you see that when I write this, I write magnetization, I apply electric field and I generate magnetization. And this coefficient alpha here basically tells me how strong is the response, right? Imagine if alpha is 0, that means I apply a lot of electric field, but I generate no magnetization. When alpha is very large, that means that I can apply a very small electric field, yet I can still generate a very large magnetization. So in other words, this alpha basically tells it's an intrinsic property of a particular material, and it describes the ability of the material to basically couple electric field with magnetization, or the ability of the material to host magnetoelectric coupling. Okay, so this alpha is described by the internal properties of the material, and it turns out that in a topological Axion insulator, not only there is an alpha, but also, in other words, not only alpha is not 0, but also alpha is fundamentally quantized by the fundamental constant of the electric charge and Planck constant. So if you know the quantized Hall effect, we know that the Hall conductivity in this kind of a quantized Hall effect is quantized by also by this actually E squared and H. But here, this is this is another example of quantization in condensed matter system. So here, what we are saying is the magnetoelectric response of this special kind of topological Axion insulator is quantized. And actually,
let me ask you that
yes.
one's got me going. So why is that, or is there a way that you can explain in words?
Yes. So you can think about, essentially you can think about, because you apply an electric field, you spontaneously generate a sort of a current that is running around the edge.
Right.
Yeah. And this current has something to do with basically the chiral edge states, like in the quantum anomalous Hall. But in the quantum anomalous Hall, you can think about, you already have this edge states running one way. But in the Axion insulator, you can think about, you have edge states running on the top surface in one way and in the bottom surface in the opposite way. So when you don't apply electric field, you get no magnetization, because you have, current running this way and current running this way. But when you apply electric field, it turns out that you can make these two unbalanced, and one of them will show up, and then that leads to this. Basically, one of the chiral edge mode will be more dominant, and as a result, this result is quantized.
And that mode is coherent, so it looks like an atom. And
exactly.
I mean, it's like an.
Exactly. Yeah. So if you think about this quantization of condensed matter, I'm not sure how many of you guys are familiar with condensed matter physics. If you think about quantum mechanics, quantization seems to be not very remarkable, because we learn particle in a box, or we know harmonic oscillator. We learn all these hydrogen electron in our quantum class. Everything is quantized. All the energy is quantized, spin is quantized. Everything is quantized. So why is it? Why is it special? But remember that when you think about particle in the box, you're thinking about trapping a single electron inside the box. Okay. So when we think about one particle, then it's described by quantum mechanics, it's quantized. That's okay. But right now we're treating a macroscopic material. So when we say there is a Hall conductivity, or there's a magnetoelectric coupling, those conductivity or coupling is not realized by one electron. It's realized by 10 to the 23 electrons. When you think about so many electrons moving together, they can bump into each other, they can do many, many crazy things. So then the response we get highly depend on details. If I make the electrons more crowded, then maybe the response will be different. Or if I put in more defects, then maybe the electrons will bump onto defect more, and as a result, my conductivity will become lower. But only in very special case, when all the electrons listen to one order, when all the electrons move in an extremely coherent way, then you can realize macroscopic quantization of 10 to the 23 electrons. And those kind of response are basically originate from topological ordered phase of matter, or topological phase of matter. And so far, actually, the only quantized macroscopic response of a material that scientists have found is the quantization of the Hall effect. And we know that it can quantize into integer or into fraction of integer, and that has won, multiple Nobel Prizes, many, many Nobel Prizes, okay? So now this quantization of the ME response would be only the second example of quantization of macroscopic response. And that can be realized essentially in this Axion insulator. And that's, by the way, the picture that I was trying to say. You apply electric field and you generate sort of a loop-like current, yeah. Okay, so now this is very interesting. So then we wanted to look for this topological Axion insulator. Theoretically has been proposed, but it has never been realized in real materials. So then what would be a good candidate of this? So it turns out that we can sort of get some idea from the theoretical works. So essentially, if we think about starting from a topological insulator, think about, for instance, the most typical topological insulator is this bismuth selenide or bismuth telluride compound. So there we can essentially think about this material is an insulator inside the bulk, but it has this metallic conducting surface states, and these surface states, they behave like a Dirac fermion. Okay, so their energy momentum dispersion is this linear kind of dispersion, light-like dispersion. Okay, so now then it turns out that we can get a Axion insulator by include magnetism inside this topological insulator, and specifically we actually want the two surfaces to have opposite magnetization. We want to somehow induce opposite magnetization into these opposite surfaces. Okay, so when that happens, then when you include magnetism, then these Dirac fermions will open up a gap. Okay, so it will become become gap, and it turns out that this gap version is theoretically a candidate of topological axion insulator. Okay, so now the question is that what kind of real material are there that we can realize this kind of magnetic version of topological insulator with opposite magnetic moment on the top and bottom surface. Okay. By the way, we also need to put the chemical potential Fermi level very precisely inside the gap. Okay. So this is, if I would show you, this is basically the topological insulator. This is its crystal structure if you look from the side. So essentially, it's a layered structure. You can see that I have every building block, I have 2 bismuth layers and 3 tellurium layers if I'm looking from the side. And this is a van der Waals material. So then there is a van der Waals gap in between, and then there's the next bismuth telluride, and so on and so forth. Okay. So now it turns out that last year, there is this new material that is synthesized, that is this manganese bismuth telluride. And we can essentially think about it as an additional layer of manganese telluride intercalated inside the bismuth telluride. So therefore now each building block has 7 atomic layers. You can count, there are 2 bismuth layers, 1 manganese layer, and 4 tellurium layers. Okay, and now there's the van der Waals gap, and then there's the next manganese bismuth telluride unit, and then the next one. So again, we're looking side view. So this is stacked along the z direction. Okay, so now why is it interesting? Because manganese is a magnetic element. And indeed, when we go to low temperature now, compared to bismuth telluride, this manganese bismuth telluride magnetically ordered. And it orders actually in an interesting way that within each manganese layer, the spins are all ferromagnetically ordered. But then as I go to the next layer, it is antiferromagnetically coupled. So then we have this antiferromagnetic topological insulator. And it turns out that this is a very good candidate of the axion insulator. I'll explain a bit more. Oh, by the way, I should be careful with the time, so I can talk until 8:15?
No.
Or 8?
8. Well,
8.
More or less, but
oh, okay. I thought this was
8:05 is good.
Okay, yeah. Okay. So then let me be brief. So essentially, what we found is that if we can isolate an even number of these manganese bismuth telluride layers, then it will be a very good candidate of axion insulator. And this is because we know that, experimentally, we already found these Dirac fermions in the manganese bismuth telluride, so it has Dirac fermions. And when we have an even number of layers, then naturally the top and bottom layer will have opposite magnetization, like what I just introduced before. And thirdly, when we exfoliate down to very thin, we can use electrostatic gating. And then as a result, we can then detect that, we can precisely tune the Fermi level inside the gap, which allows us to realize the axion insulator phase. Okay, so let me show you what we did. So essentially, it turns out this crystal is very stable when we have a piece of crystal. But when we start to use Scotch tape and to isolate a very thin layer, let's say a few layers, a very thin two-dimensional limit, then it becomes extremely air sensitive. So it becomes bad the moment that we expose to air. So therefore, we actually do the entire fabrication process, the exfoliation and fabrication process inside our glove box, which is attached to an E-beam evaporator. So we can exfoliate, and we can use this pre-made mask, and then we can put contact on, we can build a device. This is a real image of the device, okay? So, so 1 minute. So essentially, what we did eventually, it's, these are all details. Let me skip them. So
you can take 5 minutes. You don't have to.
Sure. Yeah. But let me be brief. Yeah. So now, in order to detect the magnetoelectric coupling, essentially we need to apply an electric field And then we want to search for, because the application of the electric field, it will generate a magnetization. So therefore, what we want to do is we want to apply an electric field, which we can do by the gating, okay, the electrostatic gating, and we want to measure the magnetization that is generated by the electric field. But that turns out to be extremely difficult for a very small material. So what we have here, this device, the MBT is only like 20 micron by 20 micron by 10 nanometer. So it's a very small fraction of materials. As a result, sensing the magnetization becomes extremely difficult. So we are still trying to do that, but in the work that the paper that we published, we did not directly measure the magnetization. What we did alternatively is to use the electrical Hall effect. So let me say just very briefly a few words about Hall effect. We know that what the Hall effect is, if we have a piece of metal and we apply a magnetic field, then without the magnetic field, the electron will travel straight. Okay, so I apply voltage, then the electron just travel according to the voltage defined the straight line. But when I have a magnetic field, then there's Lorentz force. So then the electron will start to bend, and as a result, I will measure a transverse Hall voltage. Okay, that's the regular Hall effect. But it turns out that if my sample is already has magnetization, oh, by the way, if you measure the Hall resistance as a function of the magnetic field, then you get a straight line, okay? So, but it turns out that if I have a ferromagnet, then the internal magnetization can replace the role of the external magnetic field. And as a result, I can apply a current voltage, and I don't need to apply external field. The internal magnetization now can bend the electrons. As a result, I get a Hall voltage. And this is the so-called anomalous Hall conductivity. And obviously, when you switch back and forth, we can also control the magnetization to be pointing up or down. And as a result, you can actually change the sign of the Hall conductivity. You can get this hysteresis loop, okay? So in other words, we say that the anomalous Hall effect can be a signature of the magnetization. So then what we were managed to do is we fabricate this Axion insulator state, this even layered manganese bismuth telluride, and we measure the Hall response without the electric field. And without the electric field, we see no Hall response at a zero magnetic field. And the moment that we apply the electric field, we see a very clear anomalous Hall effect. And this anomalous Hall effect basically is a signature of the magnetization. In other words, we probe the magnetoelectric coupling in this way. So let me just skip the rest of the details and let me talk a little bit about in general what we do. Okay. So in general, I thought I misunderstood the time. I thought it's 45 minutes. So So in general, our lab is interested in discovering all sort of topological phases of matter. So topological Axion insulator is a new example, is a very interesting example that we're trying to look for right now. But in general, what we are interested in is to trying to understand emergence in physics. So essentially, when we try to think about how we do science, there are two fundamental philosophies. One is that we can try to break things apart, right? And then we can try to go deeper and deeper, smaller and smaller pieces. We break nuclei, we get quarks, right? So in other words, this is a top-down approach. But we can also, on the other hand, given the same fundamental particles, when we do condensed matter, we don't need to care about quarks. They're much higher energy scales, right? But given the fundamental building blocks, how can they organize together? For instance, we know that we have water, we have steam, we have ice. If we break them apart, then we understand nothing because they're all H2O molecules. However, under different temperature and different pressure, they form different organizations and with dramatically different properties. And when we think about the world of electron, this kind of emergence is much, much richer. You can have so many different phases of matters. So we already know we can have insulators, magnetites, superconductors, and so on and so forth. So what it turns out, what people realize recently is that there is a parallel universe that all these kind of conventional phases of matter, there can be a topological correspondence, right? So there can be a normal insulator, then there can be a topological insulator. And those kind of topological property, like I said, it basically is deeply rooted to how the electrons move in a coherent way, listen to one order inside the material. So if we can find that, then basically it will give us new ways to control electrons at the atomic scale, and also control them in a coherent way. Now in the quantum era, we want to create qubits, and we want the qubits to have very long coherence time, and those things can all have something to do, because topology naturally means a sense of robustness, right? Think about when you make a knot, unless you undo the knot, if you just change the shape, then the knot number doesn't really change. So that's a built-in a sense of robustness, and that has something to do with how the electrons move inside the crystal. Yeah, so that's pretty much it. So I finished in 5 minutes. So I'll just stop here. Thank you.
Okay, well, thank you very much. It's interesting. You really, really put things together to get someplace new. Questions about the talk? Or more, could be more, doesn't have to be too specific, could be a general question about the.
Yeah.
I have a question. When you were talking about the magnetoelectric coupling in the topological Axion insulator being quantized, that was a result of the property of the material, like the alpha. How do you know that?
You mean experimentally, how do I detect that, or theoretically? Yeah. Okay, yeah, so it's a similar idea, right? So essentially we need to know how much electric field we apply, and we need to very precisely measure the generated magnetization. Then then M divided by E is the coefficient, and then we can measure the coefficient. So that's what we're trying to do. It's a very challenging experiment due to multidimensional constraint, the size of the sample, the need to control many parameters very precisely, and the difficulty of sensing the magnetization when the sample is too small. So we're trying to basically find the correct configuration of experiment that can satisfy all these, and as a result can sense this very precisely. That is still ongoing, yeah.
Okay, so then ideas, because alpha is quantized, that's like special because that's quantization on a macroscopic scale, right?
Yes, yes.
Okay.
Other questions?
On one of the later slides, you had a picture of like the laboratory setup, and you only showed it real quick because you skipped through it, but I completely do not understand what was happening there and was wondering if you could say a couple words about it.
Good.
Oh, you mean the setups?
Yeah.
Okay, so in our lab, we have a few different, so we have, the lab is fully set up. So basically, we have, we have this device fabrication facilities. So essentially that allows us, most of the materials we study are, the method that we do is very similar to what people do on graphene. So we use Scotch tape to exfoliate down to very thin, and then we try to attach contacts and gates and stuff like that so that we make a device out of it. But the difference with graphene is that graphene can do everything in the air. So it's very stable, it's very robust, it will not change. But in our case, we need to do it in a very protected environment. So there's a glove box. So inside it has basically water and oxygen level less than 0.1 pp part per million. And this is filled with ultra pure argon. So we do everything inside this glove box. And we also attach the contact and everything inside. And once we make the device, then essentially we are pursuing two kinds of experimental measurements. One is basically ultra low temperature transport. So you pass a current and you try to measure voltage and things like that under very low temperature. The dilution refrigerator goes to like millikelvin, 15 millikelvin. This one goes to about 1.8 millikelvin. So then that's quantum transport. The other direction is we try to study the optical response. So for instance, we do Faraday rotation, Kerr rotation, second harmonic generation. So essentially by using laser and look at the light matter interaction, we can also learn actually at very low temperatures. So then there we can also learn a lot about the electronic properties of the material. So that's essentially experimentally what we do. Yeah.
Thank you.
Nice. That's what you've been doing in the last year.
Yes.
A lot of work. Maybe one last question. Okay, if not, thank you very much. Really impressive work, particularly, I mean, you're getting going quickly. It's great, great to see. Thank you so much.
Yeah, thank you for the invitation and very nice to meet you guys. Yeah, if you have other questions or if you're interested, please send me an email and we can chat more. Yeah.
Thank you so much.
Bye-bye.
Thank you.
Thank you.
Good to see you, Professor. Thank you.
Yes. Thank you.